The James Webb Space Telescope is disturbing the apple cart out of nowhere. We understand that we might need to revise every single textbook about the start of the universe. Well, that's the issue. Renowned American physicist Michio Kaku expressed a year ago, everything is in a fit because of the James Webb Space Telescope. It has recently come to light that we might need to amend every single textbook regarding the subject of how the universe came to be. A galaxy like our Milky Way, which has 100 billion stars and is billions of years old, requires a tremendous amount of time to form. It takes ages to create a universe like the Milky Way galaxy. However, the James Webb Telescope has discovered 6 galaxies as extensive as the Milky Way that existed within 500 million years of the Big Bang. The James Webb Telescope has identified 6 galaxies that existed 500 million years after the Big Bang and are as large as the Milky Way itself. This isn't something we expected. Early galaxies younger than 500 million years shouldn't exist if they are larger than our own Milky Way. If they do, we have an issue, and we may need to reconsider how the universe came to be. Something doesn't add up, and we may need to reevaluate our theory of the formation of the universe. Astronomers are currently experiencing a period of abundant discovery nearly 2 years after the James Webb Space Telescope's successful launch. As the instrument continues to expand the limits of observation, astronomers have also encountered a plethora of new mysteries. The initial 500 million years after the Big Bang were the focus of the telescope's observations, and not long ago, it found galaxies that are far from primitive, much more massive and developed than previously expected for such early epochs. Now, researchers are looking into a galaxy that may be among the oldest ever observed. What's more shocking is that it already has billions of stars. The Hubble Space Telescope spotted this giant celestial body as a curious dot of light in its field of view just 2 years ago. Before directing the James Webb Telescope to examine it, researchers couldn't understand that this particular dot of light was actually a massive galaxy on the brink of time. The spot of light turned out to be a primordial galaxy, far bigger and astonishingly old, according to Webb studies, with a redshift of Z equals 9.3, or just 510 million years after the Big Bang. We can observe this galaxy, known as GZ9P3. Despite having identified several other early systems, this finding continues to amaze scientists. 35,500 m after a huge explosion, none of the objects have been seen with a size similar to this one. These outcomes suggest that the system's stars formed at a faster and more efficient rate than previously thought, reaching its current size. Not only that, but GZ9P3 has a strange shape that might reveal early-stage cosmic secrets. 2 bright spots within the galaxy, which the Discovery team interprets as signs of 2 dense cores, point to a possible galactic merger, suggesting 2 early galaxies may have collided in the early universe. Additionally, researchers determined the shape, age, and mass of this ancient galaxy and focused on its stellar population, finding the image dominated by young, bright stars along with the older stars of GZ9P3. The JWST allowed the research team to detect elements such as silicon, carbon, and iron. Star explosions release iron, the heaviest element a star can create, into space, enriching the early universe with metals that later form stars. It was also found that GZ9P3 contained a larger number of old stars than anticipated, suggesting galaxies reached chemical development faster than previously believed. Stars may have formed much earlier and aged enough by this cosmic period, challenging our current understanding of galaxy formation. Considering these results, a new model might be needed to explain the large size and chemical maturity of galaxies and their rapid progression into these states. They suggest that right after the Big Bang, galactic mergers might have been the most common cosmic event. These galaxies are more massive than previously thought possible. Though our current cosmological framework may not be incorrect, our understanding of the rate of galaxy formation likely needs updating. Our cosmological model is based on mathematically supported ideas and data, but there are still hints that something may not be quite right. The crisis in cosmology is a term you may be familiar with. This issue arose when different methods of calculating the expansion of the universe started to produce conflicting results, and they still do. Cosmologists are unsure because recent findings from the James Webb Space Telescope have worsened this situation. Due to cosmic expansion, distant galaxies are receding from us. When we use the cosmic microwave background, CMB, the light from when the universe was just 380,000 years old, to calculate the rate of the universe's expansion, we get one result. Another method, comparing the apparent brightness of distant supernovae to their expected brightness, known as the traditional light method, gives another rate of expansion. This rate is called the Hubble constant. Conversely, the cosmological crisis includes the Hubble tension, the discrepancy between the two findings. However, this is not the only crisis. Our theories are being pushed to the limit by a new cosmic enigma. A lifetime of refining a single hypothesis about the universe is now being questioned. This is precisely how science advances, and I am in favor of it, commented Kaku. Endless stars can be seen when one looks up at the sky, as long as they aren't in a city affected by light pollution. The Andromeda galaxy, appearing as a faint dot among the stars, may be visible. Planets, galaxies, and stars abound throughout the universe, so their size relative to the universe is an open question. Just how much matter is out there? Current cosmological observations vary on the distribution of matter in the modern universe, which typically causes this problem. A new cosmological dilemma, the mysterious S8 tension, has emerged from this. The clustering or unevenness of matter in the universe is measured by the S8 tension. To visualize it, think of space as a massive jigsaw puzzle with pieces of matter everywhere. The distribution and clustering patterns of this matter are of interest to researchers. Two measurements can be used to assess this. One approach is through observations at low redshifts, like those possible with weak gravitational lensing, where light from farther away is bowed and twisted by the tremendous gravitational pull of enormous objects like galaxies and black holes. The subsequent approach utilizes the CMB-based standard model of cosmology. The S8 value that arises from these two approaches, however, isn't consistent. At its confounding core, the S8 tension is this discrepancy. Our next step? Even with all the theories, observations, and constructs that back them up, something is clearly amiss. A massive, infinite simulation, run by one of the world's most powerful supercomputers, helped scientists fill in the gaps. Over 50 million hours of computer time, spread across 30,000 processors, were required for this Flamingo project. A somewhat puzzling term, Flamingo stands for Full Hydrodynamical Large-Scale Structure Simulation with All-Sky Mapping for the interpretation of future observations. Despite representing only 20% of the universe's mass, conventional baryonic matter is included in Flamingo, unlike past simulations that exclusively considered dark matter. Flamingo tracks the effects of both dark matter and the cosmic winds caused by supernovae and supermassive black holes, which may slow the expansion of galaxies. Even though Flamingo achieved a lot, such as accurately predicting how the Milky Way and Andromeda galaxies formed, it couldn't resolve the S8 tension, which was its intended purpose. In fact, the simulation contradicts what Webb and other telescopes have observed regarding the distribution of matter in the universe. Today's model provides a promising explanation for galaxy evolution, but it has a flaw. It suggests that the actual density of galaxy clusters is 7% lower than what is observed. There is still a 5% excess clustering in the Flamingo simulations, regardless of how detailed they are. The Hubble tension is real, according to recent observations from the Webb Space Telescope, which lend credibility to the results obtained by the Hubble Space Telescope. The so-called Hubble tension is worsening because Hubble's estimates of the rate of the universe's expansion are correct. The main issue is that the Hubble constant, a measure of the universe's expansion rate, doesn't match any of the available data. While the exact source of the discrepancy remains a mystery, some theories have suggested that new physical principles might be needed to resolve the apparent paradox. Now that we can rule out measurement errors, the intriguing possibility that we may have misunderstood the universe lingers. New ideas keep emerging all the time. Some even suggest doing away with dark matter entirely. Could you leave a comment with your thoughts? Then hit that subscribe button.